Okay, welcome to part 4 of our lecture video series from Monday, April 24th, where we are discussing now heat transfer and specifically what that relates to enthalpy at constant pressure for any kind of chemical system. So to kind of wet our whistle, so to speak, when talking about heat transfer, let's just kind of practice this idea of heat transfer just between objects so that we can then move on to talk about heat transfer between or as a result of molecules reacting in some kind of like chemical reaction as being our chemical system instead of just looking at molecules. And from there, we will talk about what that means for this idea of the enthalpy of reaction coming up. So let's start with an example of looking at heat transfer between objects. So I have told us here that we've got a 248 piece of copper that is dropped into 390 milliliters of water that is at some temperature 22.6 degrees. So that is a lot of information. I think I'm going to draw this out to figure out what's going on. So I've got a piece of copper, and I know the mass, which is 248 grams, and that is dropped into some sample of water. That is at some initial temperature of 22.6 degrees Celsius. Okay, we know that some heat transfer happens such that by the time our heat transfer has completely finished, meaning some thermal equilibrium has been established between our copper and our water, meaning there's no longer a temperature difference between these two materials. I know that let's see here, what do I say? The final temperature of the copper water system is 39.9 degrees Celsius. So now let's get into the meat of the question. What is the question actually asking us? So if the specific heat capacity of copper is 0.385 joules per gram degree Celsius, so I'm going to go ahead and write this here. What is the initial temperature of the copper? All right. So let's think about what's going on here. So from the looks of it, I had water that was at 22.6 degrees C, and then the addition of copper caused the copper water system to have its overall temperature raised. So this means that I had to have dropped some kind of hot or hotter, at least than the water, piece of copper into my water. So let's start, I think, by thinking about how that heat is transferred. So I know that my copper had to have been at a higher temperature. So when that copper is placed in water, it is going to release heat such that the water absorbs it. And we're assuming that no heat is lost into like the beaker or the atmosphere. We're assuming it's a perfect heat transfer just between between the copper and the water. So we're assuming that all of the heat lost by the copper is going to be equal to the heat that is absorbed by the water. So let's whip out our MC delta T equation. So for the copper, that's going to be negative mass copper times the specific heat of copper times the change in temperature of the copper. And that's going to be equal to the mass water times the specific heat of water times the change in temperature of the water. So let's see if we can't start plugging some things in. So the mass of the copper, we were told that the copper weighed 248 grams. So negative 248 grams. And then we were also told the specific heat capacity of water, which is 0.385 joules per gram degree Celsius. And then we have this delta T, which is final minus initial. So we know that once the copper has fully cooled, it's reached this thermal equilibrium with water, which is 39.9 degrees Celsius, minus whatever its initial temperature was, because this is what we're trying to solve for. This is the unknown. All right, so this is the amount of heat lost or heat released by the copper. So then what about the water? So this is going to be the mass of the water times the specific heat of water times the change of temperature of the water. And let's look at what we know about our water. So let's see here. I know that I had 390 milliliters of water. So if I'm going to try to plug this into MC delta T, I need to convert that into a mass. Luckily for us, remember water's density is 1.00 gram per mil. So if I have a volume of water, then we can go ahead and assume, at least for now, that its density is 1.00 gram per mil. I'm going to be a lot more picky about this, thinking about the temperature dependence of density coming up for us in future experiments. However, for now, it's all right to say that since we have 390 mils, then we have 390 grams of water times the specific heat of water, that is 4.184 joules per gram degree Celsius. I didn't write this down because it's something I knew. Again, I will always provide for you specific heats, but the one for water is a good one to just know. And then we need to multiply this by the change in temperature of our water. So the final temperature of water, again, is going to be the temperature that the water was brought to upon reaching thermal equilibrium with our copper. So it's our 39.9 degrees C, minus the initial temperature of the water, which I was told is 22.6. Ignore all this down here. Oh my goodness, so much extra work that I don't want. Okay, so let's see if we can't put these pieces together. So I'm going to start, I think, the way I like to do this is chunk it out. So I like at least getting the product of these two terms on each side. So again, just rewriting that the heat released by the copper is equal to the heat absorbed by the water. So here on the left, I've got 248 grams times 0.385. 248 times 0.385. All right. When I do this on my left-hand side, this becomes 95.48. Let's think about our units here. I got grams to cancel, but this leaves me in joules per degree C. And this is times my 39.9 degrees C minus my initial temperature of copper. So this is my heat released by my copper. That is going to be equal to the heat absorbed by my water. So let's figure out the product of these two terms. So our 390 grams of water times our 4.184 joules per gram degree Celsius. This gives me 1,631.76. And again, we've only got grams that cancel. So that's joules per degree C. Now times the temperature difference, so that's my 39.9 degrees C minus 22.6 degrees C, that is 17.3 degrees Celsius. And to make my life easier, I'm going to simplify this right-hand side, and then I'm also going to distribute this constant. You know what? No, that doesn't seem easy to me. Let's just wait. So I've got now, oh yeah, what I'm going to do is I am going to move this negative over. So divide both sides by -1. So I have 95.48 joules per degree C times 39.9 degrees C minus initial temperature. That's going to equal to negative whatever this product is. So 1,631.76 times 17.3. This gives me 28,229.488. Again, my fully unrounded value. Okay, let's look at our units here. Degree C per degree C. This gives me joules. And if I'm going to try to solve for my initial temperature, I want to get this by itself. So how about I divide both sides by this guy here. So divide by 95.48 joules per gram degrees Celsius over 95.48 joules per gram degrees Celsius. I will now have 39.9 degrees C minus my initial temperature is equal to my negative 28,000-ish over my 95.48. This gives me negative 295.75. And now let's look over here. So this is joules over joules, leaving 1 over, right? So we've got here 1 over gram degrees C. And I don't know why I keep adding in a gram when there's not one. So 1 over degrees C. So this would be degrees Celsius over here on the right. All right, subtracting my 39.9 degrees C from both sides. This gives me negative T initial left. So then we've got to add a negative, so this is going to become more negative. This becomes negative 335.65 degrees C. And then just dividing both sides by -1, I get that my initial temperature of my copper had to have been, and then let's check our sig figs here. Looks like I've got 3 sig figs all across the board. This would have to be 336 degrees Celsius, which would be the initial temperature of my copper. And we told ourselves that the copper had to be hot in order to warm the water. And is that true? Yes, looks like it's true. And you can always plug this back in to make sure that it kind of matches the math that you've done. And I think what I'm going to do for today is just look at some heat transfer practice like this. And then we will move on to the heat of reaction, which does involve heat transfer. Just I think it deserves a little bit more time than what I have left for this morning. So we can start calculating the enthalpy of reaction. Starting up on Wednesday. So that will be the, let's see here, 26. Okay, so that is all I have for you today. We will, like I said, move on to heat of reaction, or the change in enthalpy of a reaction, and the various ways that we can calculate it, coming up on Wednesday. And yeah, we will be living in the land of heat transfer, like so, coming up here after this exam week. So I will see you tomorrow in lab for our review. Have a good one.